Okay, so today we are going to be discussing the paper debates. Does information theory provide a new paradigm for earth science? And the moderators for this discussion are going to be Luis and Andrew. So let's go ahead.
Okay. I would like to share my screen. I have a few slides with my summaries. So this way I can compare, and well, this is my best understanding about the paper. If I have some issues, you can tell me. Okay. Can you see my presentation?
Yes.
Yes.
Okay. Okay, so from my point of view, we have a problem, an issue in the nature that we want to characterize. And the only thing that we know about that is the information that we are collecting from that problem. And this information plus some models we are we can understand better the problem, we can do prediction, decision making, and create hypothesis testing. So the common example of that is the elephant. Oh, I'm going to use this. The elephant, where each person really is trying to guess what is happening, and each one has different opinion. So from my point of view, really the phenomenon here is the elephant. We have some characteristic, and each one has some characteristic related with tail, the trunk, the leg, ear, and we have some models. So each one has different model that can be useful in different situations. So the question that I have from that is, okay, how much information was captured from our models? So for me, this is the idea that each one of these models in some way could be useful, but you need to know how much is or when you can use it. So you need to quantify this information. And the other question that I have about it is how probably our knowledge is correct, because maybe we can use this model and we can try to predict something in the elephant and maybe can work, cannot. So there's some probability of we are going to be right in the prediction. Then we have some background. So there are some definition or some ideas. So the first one is the idea of the example of the velocity versus the position. So the really is not the same. But in some way, we have the probability to find the particle. You have a yes, no answer. So you are defining a bit, a 0 or 1. But in the moment that you find the particle, you have some work that is available. So somewhere you are defining some energy. So between a bit and an energy, there are some correlation, some relation. The other idea is the information. So the definition in some way is the surprise. No? In some way, I like this idea because it's very clear that you can feel it in some way that, okay, you have a lot of surprise with some event. So it's because you are getting more information from that. And the entropy is just the total information that you can have from the phenomenon, but it's the weighted surprise because we are using the probability. But in some idea, the idea is that entropy really is the total information that we have. And for the same idea, if we have different model or different distribution and we need to define which one is the best, the general idea should be, okay, use the model that more information gives you. So my opinion is, okay, so what we are doing is believe in what more information gives you using the known data. So for this reason, I like the idea of surprise because it's very clear. Then we have some idea about the laws of physics. So the laws, or what we understand for laws now, is just information. It's just the information that we have been collected from all the past, and we put all this information in some statement, but really is our best representation of the nature. And this could be good or bad in some idea, because in some way it's defining a framework, but it cannot define everything inside of the system. Because when you follow some specific law, maybe you are following just the energy, but maybe there are some information that is a flux of information for another side of the system. So it really creates a framework, but it doesn't give you all the information, all the what's happening inside. The other idea is that information has two behaviors. One is physical, so it's what kind of thing exists or what is real, and it's the idea that it's the basic to understand the world. So it's what we can know and how we can know it. So the information has this both behavior. Then we have the benefit of use the information theory, and there are 4 questions, and here I have my answer, so this is my opinion. So first we have that, can information-based approaches better inform the development of Earth system? My answer is yes, because we are defining a stochastic framework to find the relationship. The other is, can we characterize the information content of model? My opinion is yes, we can quantify this information, but the problem is how, because we don't know the real distribution of the data. But I have an idea where maybe we could learn it in some way, because now we have machine learning techniques. So maybe we can try to learn the distribution, and this way should be a good way to have the total information in some model. The other question is, can natural system dynamic be represented and predicted using information theoretic form? Yes, because we can learn the structure and we can learn the function. So in some way we can create the representation of this system. Does information have a role in deterministic categorization? And my opinion is yes, because information theory should allow us to discover a stochastic representation of the system, and the main representation or the expected value in some way could be the deterministic representation in a physics-based model. So really, we are talking about the same. So deterministic is going to be some specific, but really we can characterize everything in a stochastic way. Then we have the cause and effects paper. So here we are talking about the fluctuation. So this is a way to characterize or recognize what is the relationship between different variables, because there is an asymmetry in the variables. So this way we can quantify the cause and effects interaction. And for that we have 4 tools. One is the transfer of entropy, that is quantifying the reduction of uncertainty given the path of some variable. Then we have partial information decomposition, momentary information transfer, that here we are quantifying how strong is this relationship between the path and the actual variable. The causal history approach is quantifying the total influence from the past in the present. So in some way we are characterizing all the relationship in the system. And all of this we can use it in a non-interventional approach. But exists the option that you can do it in an interventional approach, and in that case you will have some idea that the hypothesis testing, because you are forcing the system to do exactly what you want. But if we want to do that, first we need to quantify the information. So how much information do we have in our model? So here in gray, in some way it said that machine learning could be a benchmark for a physics-based model. But my question or my opinion here is, okay, any machine learning algorithm works? Or why not choose the best model versus the other? Because in some way, each model is learning with different amount of information. So the idea is that we should try to extract information, and each time that we have a model that has better performance, in some way is learning more. and we should try to extract this information. Other idea is that the ensemble would help only if the model structure is randomly selected. In general, we are using the ensemble model, but really we are not changing so much the structure. So if we don't use a random structure that is in some way machine learning is using, or you are using a physical model, but you are not changing so much the structure. So really you are not reducing the structure error. So you have to have this kind of idea of the random structure. Another idea is that the model performance has two behavior. One is the predictive accuracy, is that what we know, and the functional accuracy is what we don't know. So for me, at least, this here we are talking really about generalization. Is when you try to apply your model in another scale, another area, another part of the world. So if we have a model that with a high functionality accuracy, then you could apply hypothesis testing in a meaningful way. Then we have another paper about the information theory and the relationship with the physics. This is, at least for me, was a deeper topic. But they said in the paper that, okay, we have some statistical thermodynamic that quantify the entropy like a microstate aggregated. Then we have information theory entropy that quantify question. So how many questions you need to characterize the system. So in some ways it's information. And for the same idea, the entropy can be measured as an uncertainty or a physical quantity. And if we use kinematic geometry, can be used to connect with statistical thermodynamic and information theory to characterize state variable and momentum. And the other interesting idea here for me was that there are some variables that could be dynamic coupling, or that is different than evolution. So there are variables that can be correlated, but the system does not evolve. So my question is, do our models allow to evolve really, or we are creating a model that has a very strong structure that really we are just moving one variable and one could go up and the other go down. So really, we are not really allowing to the system to evolve. And finally, we have the paper about the complexity. So here said that science and modeling use data compression to discover patterns. So in some way, what science is doing and modeling is doing is the same, because we are trying to compress the information to have what is most useful for us. And model performance and complexity must be considered together to generalize and make prediction. So in some way here, we have the idea of the parsimony. So we should try to use the model that has the lower complexity and the highest performance. And now we have two kinds of models: the machine learning approach that to be in general they have a high performance, and they have a high complexity. But in some way we have a minimal compression. And for the other side, we have a physics-based model in general that has lower performance, lower complexity, but we have an overcompression. So in some way, we should try to find a solution where we have the best of the both. So we have to find something in the middle. The other idea is that the information content in the could be quantified in some way, measuring the size of the program. This is a nice idea that, okay, it could be, because in some way, yes, if you have a more complex program, in some ways, it's because you are having a more complex system, or the more complex description of the system. So in some way, you have some idea of the information inside. And this way, you could use this metric to use hypothesis testing. This is an idea. final idea is that quantifying information content is any comment? Hello? Can you hear me?
Yes, we can now, but all of us, we were having issues hearing, we were hearing a very weird noise, but I think, yeah, something went wrong, but it seems to be better.
Okay, but this problem was middle of the presentation?
No, it wasn't. No, it
Okay,
was
at
just
It
at
was
the
right
end.
towards the end, actually.
Yeah.
Okay.
Oh, it just started happening again.
Yes.
Ocean, can you mute? Because
Ocean, this seems to come on when you're speaking. Is there something at your end? Yeah, Ocean, it goes away when you're muted.
Ocean, is there any way you can not use your headphones? So maybe it's a problem of communication of the Bluetooth.
How about now?
Yeah.
No, no, it's okay.
but Louise, you were cutting out before that anyway. So
Can't hear you.
like you were kind of frozen. So maybe if you repeat the last little bit of your presentation, that'd be good.
Okay.
Can't hear you, Barb.
What about other people? Can you hear me?
Yes, I can hear you.
Yes.
I can hear you as well.
Yeah.
Okay. Where? From here, maybe? No?
Just the last slide, I think, unless
Okay.
anyone else.
Yeah, I think it was just the complexity slide.
Okay. No, here, what I was trying to say that really science and modeling, both are using the compression. So in some way, they are doing the same. And we should try to use a model with high performance and a lower complexity. So we have the idea of the parsimony here. And we have two approaches now. We have the machine learning that has a high performance and high complexity, but really we have a minimum compression. And we have a physics-based model that has in general lower performance and lower complexity. So we have an overcompression. So we should try to find a model really that is in some way in the middle of both. So this is something that in the future we should try to find, or mix at least the best of the both. And the other idea in this part of the paper is the information content could be measured using the size of the program. So in some way, if the code is so long, so in some way it's taking more line to represent the model. So in some way you have more information inside. So this is a kind of idea to content to measure the information inside. And for me, at least, the last sentence is that the quantifying information content is essential for everything that we want to do first. This. Any comment?
That was a great presentation. Thank you.
Thank you.
Yeah, I agree. That was a nice overview of kind of the different components of the paper and the other debates papers. And I'm curious if anyone else has any other sort of like main takeaways or any of the sort of 4 components that really jumped out to them in this paper that like really interested you.
I think one thing that was interesting to me is, the idea of maximum entropy production, and the more surprise you get from information, the better. And I just can't help but take that to an extreme about something like unknown unknowns. And if you are flipping a coin with heads and tails, and it lands on 5, for instance, and not heads or tails, does that still produce maximum entropy when the surprise is something completely outside the distribution?
Well, if you get an event that you had not allowed for in your previous characterization of the system, and something happens which is outside the set of all your possibilities, then that's your maximum surprise. So clearly, clearly that's the most informative type of event. The question that arises is that very often what happens is when that happens, what people do is they ignore that event because it doesn't conform to their preconceived notions of reality. And so an example of this was the hurricane event that happened in Japan, which resulted in the nuclear reactor being destroyed and then contaminating part of the island. Big Baker gave a talk about the fact that there actually was evidence of a hurricane tsunami of that size or larger having occurred in the past, but it didn't fit into their planning and cost estimates, and so and so it was essentially ignored.
Yeah, and I think that also kind of ties into the last part about the difference between the complexity of the model versus the physics-based and data-based approach, where at some point we just can't use all the information that we're given in a data-based approach. And so, if we have thousands of years of record to make predictions about future hurricanes scenarios, maybe we can't find a data-driven approach that'll fit all of those scenarios. So, it's kind of always been what I've always heard is that's why you need a physics-based approach. And I think finding that middle ground between the physics-based and database will be, really key using all the information you can, but also.
So I have a question for you, Jonathan. What do you think is foundationally or fundamentally different between a database approach, a so-called database approach, and a so-called physics-based approach?
I think the ability to leave out previous data but still represent it. So if you have a physics-based approach that you don't need to have a record of every past event, but you can still represent that with your future prediction. And specifically like taking a derivative taking a derivative, you can make a prediction at every time scale and every temporal scale, because you can fill in the gaps.
That's a math operation, but I think if Stephen was here, he would argue that physics-based approach is fundamentally a representation of everything we've learned from the past. So it's a synthesis or a summary of all of the information in the past. So it's not entirely clear to me what the difference is, except that in one case you've done a compression, in the other case you haven't.
Yeah, I think I would follow up on that and sort of say, I think it's interesting that we often describe these machine learning techniques as high complexity, when I'm not entirely convinced that's true. We're just not necessarily representing the model in the simplest way. It would be like if every time you wanted to do, for instance, some kinematic equation for throwing a ball, that you had to write out all 500,000 terms of the Taylor expansion of that function. So in some sense, I'm not convinced that we really understand the complexities of our various models.
So if we could do what Stephen proposed, which is to measure the amount of bits required to represent the machine learning model, we could then put a constraint on that to minimize the number of bits required to represent it using machine learning. Right?
Yeah, I think you might add a parameter there, which is the acceptable loss from your compression. So if you're willing to accept some loss from your compression, I think that kind of adds a whole nother argument to that idea.
So I can ask a related question. I mean, this is a really interesting but a non-trivial topic. Could we predict the outcomes associated with the pandemic based on physics-based approach?
No.
You recall that Grace sent around a video by, what's his name, Susskind, Leonard Susskind? What I found interesting in that video was his characterization of entropy as missing information. The things that you don't know or you cannot know.
Yeah, no, I am very intrigued by this paper. I just put it in the chat there. It was published a long time ago, 50 years ago, where Anderson argues for more is different. And it's probably one of the foundational papers of complex system science. Complex system science goes much earlier than that in there. And I think there is a duality. It's not so much that one represents the other, but there is a duality of characteristics between the physics-based approach and the database approach. I mean, our physics is informed by data to a large extent, and the more the data reveal, the more we tweak our physical understanding. It depends on the level of narration that you want to achieve from these physics-based approaches, right? So the question is, when are we going to say, okay, this physics-based approach is sufficient? And that will depend on the purpose. So does the purpose guide what is important in terms of physics-based versus database? Or they are fundamentally linked but offer two different views of the world with a lot intersection in there, right? Because there's a lot of physics-based approaches which are theoretical and they predict stuff like quarks and other stuff which were not observed before, and then they are found to be true, right? I mean, they've since been observed. So the theory is informed by past observation, but it also tries to predict what is possible. But at the same time, there's the other side of the story too, right? So I think there is a duality, and we often, because we are divided into camps, we try and see, well, one is the same thing as the other, but in a different form. And the question in my mind is always, how do you comprehend this duality? What does it represent? And how do we get to it?
It seems part of what I'm struggling with in my head is how much of the data and what we perceive and what we're looking at is guided by the boundaries that we put on it, and how much of it is entirely probabilistic versus deterministic. Because at some level of physics, F equals ma, and there's not really a lot of stochastic aspect to that. But in other aspects there are, and to the example of the tsunami, and we do some of this with risk analysis, just because something hasn't happened in the past doesn't mean that it won't. So there may be some finite probability of an event, and even Louise touched on this with expected values as well. And just because there is an expected value doesn't mean that something could occur outside of that. So I guess what I'm asking is how much is everything probabilistic at some level, and to what extent does it collapse into forms that we can work with it on a more usable level? If that makes any sense. Over.
Yeah, I think I kind of have this idea that kind of addresses all three of those ideas, going back to Hoshin's first question about physics versus data-based approach. If you're in Praveen's idea about the goal of the approach is, if you're shooting a cannonball and you just want to know where it lands, you can take 1,000 cannonball shots and come up with an understanding of, if you shoot the cannonball with these initial conditions, it'll land in this area. But then what if you actually want to know the trajectory of the cannonball and want to know if it'll hit, a missile or something? So your data-based approach won't provide any insight if your cannonball is going to hit a missile if you've trained it to understand where it's going to hit the target. And so I think that's kind of that duality of data-based and physics-based approaches, and maybe what the goal is. And then bringing that to stochasticity, you can develop a physical theory about shooting a cannonball and understanding the trajectory all day long, but then what if you shoot a feather out of a cannon? Then your physics are not going to represent the trajectory of the feather very well, because there's so much stochasticity there. So I think that all breaks down. But Hoshin, that's kind of where I was trying to go with the idea of physics versus data driven, is you can, with the physics-based approach, you can see the whole trajectory of the cannonball.
Yeah, but don't forget that physics theory is incomplete until it's been tested, right? So physics is not independent of data. You take the data and then you project it into a lower dimensional space, and we call it physics. It's a particular kind of a projection. And then the physics allows us to interpolate between the data points or extrapolate outside of the range of the data, right? So I have a hard time seeing physics as anything more than a mind projection, which I use as a compressed representation to try to summarize the patterns that I see in my data. But with one caveat, that I want to do that projection in such a way that I can take what I learn in one situation from one data set and apply it in a completely different situation with a completely different data set. So it has to be generally applicable. It can't be just specific to my problem.
So just like adding on to like Hoshin's comment about, Jonathan's comment about the cannonball. So if you consider the cannonball, like if it's following the sort of the laws of physics, of projectile physics, but if you like blow up this problem to a more like higher dimensional, like complex problem, is the cannonball like, is it just like a metal ball, or does it have, let's say, something inside of it that a human can influence to sort of like, you know, diverge it from its original path? So how do you like use physics to like sort of account for that like human factor, or that like sort of those interventions? So I kind of have this, when I'm doing my work with topic modeling and natural language processing, and like I'm using generative probabilistic models to predict like, or so to understand like what topics are trending right now in hydrology, and how this will be shaped in the future. I cannot use any sort of like a physics-based approach. It has to be a data like based approach. And in the future, if we want to combine, let's say, earth science models with like physics-based models, we have to consider the anomalies and the human interventions into the model to make it like more reliable, robust, and like sort of more like believable. So yeah, that's my 2 cents.
Kavin, do you hear me?
Yep.
Okay. I was wondering about the duality. So how I see at least is that with the physical models, or in a pandemic situation, for example, with biological models, people try to understand what is going to happen, but in the meantime, you need to predict. So this is basically why the data are being used to predict, right? So for example, it's supposed that if I am doing the quarantine and I am from a risky country, I'm not going to spread the virus, but maybe because if I have a negative PCR when I leave the room, actually, I can face someone that was asymptomatic but has the virus. So I see the duality, but I think that the key challenge now is, and the future challenge is, to introduce physics into the database models. So the main problem maybe is that we need to accept that our theories are not correct for the Earth systems models.
Yeah, I like Hoshin's description of our physical models now as kind of mind projections, because in some ways that's what they are, right? Like and the reality is that over our careers and over the last few hundred years, we've developed a huge set of tools to actually deal with, to manage these mind projections. Like all the mathematics that we have and so on are basically geared to kind of help with that. And we don't really, at least not for me, and probably for most people in earth sciences, we don't really have the same toolkit for dealing with these more machine learning or data-driven approaches or the information theory. So it's kind of hard to see the models that we develop that way and combine them in the same way, right? I could, like, to come back to Jonathan's example, I could basically take my mind projection of how a trajectory works with the one that you know is used to describe friction, and come up with a new model that actually includes friction and the trajectory. But that's hard to do when I just combine two data models. At least for me, it would be at this point. And maybe that's generally the case. But I also think we have to keep in mind that, like, with these mind projections, these physical models that we have, in many cases, we actually filter the problems that we investigate to match those models. Like, what I mean is, like, in many cases, we say, like, wow, that's really too complex. Let's simplify it to this way. And then all the rest we call noise or unexplained or something like that. But, like, a lot of our what we call physical models aren't actually all that good at describing what happens in the real world. They're good at describing this idealized physics that we've developed. But, you know, our hydrology models typically aren't really all that good. I mean, and our physical models typically do not outperform, in both the sense of prediction and simulation, the ones that are more conceptual or more data-driven and so on. So I think it is interesting that, like, in these data-driven models, you can kind of build in more, you can kind of reason about this uncertainty better than you can in a lot of the more physical models, where this uncertainty is kind of tacked on at the very end. Like, so I mean, for me, who comes out of the world of you know, developing models and trying to do physical modeling and so on, I think it's actually really interesting to see these new approaches, even though I'm kind of totally new at, you know, how to actually use them. That's why I'm in this group, I guess.
Bart, I wonder if it's worth acknowledging that there's at least two classes of models that we build when we're building machine learning models. And one class is models that have internal state variables. So you just feed it inputs at the current time step, and you use internal state variables to track the memory of the past of the system. And then there are other representations where you use number of past inputs to represent the missing information about the memory of the system. And we can easily get confused if we equate these two. I mean, there's a mapping from one to the other, but physics-based models tend to be models which are Markov process state space representations. And a lot of the machine learning models are not.
Yeah, although some of the machine learning models do allow you to have an internal state, right?
That's right, that's right. But we shouldn't, I mean, we should be careful when we're doing our comparisons.
Right, sure.
Yeah. Because the meanings are different.
So I think that actually brings up a good point that we can maybe tie back into the paper in two different ways. The first is the idea of cause and effect, and that sort of implies some sort of temporal asymmetry, not necessarily captured by some state variable in sort of the framework of say transfer entropy, but there's also sort of a connection to the sort of complexity of a model that has that sort of state variable, where, as you said, Hoshin, there is a mapping where you can unroll it through sort of a separate time state to get, or a time dimension to get rid of that internal state. But I wonder if, you know, either of those sorts of ideas could be used to say something meaningful about our approaches to modeling.
So I have a related comment that takes us all the way back to, sorry, I didn't realize I didn't have my video on. It kind of goes all the way back to talking about surprisal at the beginning, and something that Bart said, now I can't remember what it was, made me think about it. So I spent a lot of my PhD agonizing over how to make a PDF out of data, and, you know, was I doing right by my data when I make a PDF using some certain method. And I got to this point where, well, I gave up on that. You know, you're just gonna have to settle for a PDF at some point. And then I decided, that I wanted to generate PDFs with certain properties, with certain information theory properties that match something I was looking for. So instead of saying like, you know, how much information do these sources contain about this target, I wanted to create a PDF that I knew represented those different information components, and then generate the data based on that PDF that I created. And I kind of quickly realized that anytime my probability was 0, so anytime that, you know, anything is so surprising that we've never seen it before, you kind of get into a hole when you generate data based on that PDF, because you can get into a state and you can lock yourself into it, because you know, you're not going to be able to, sort of like a Markov chain thing where you can't get out of that state. You know, so then what I had to do was make everything a tiny bit probable, you know, just so that you could account for that possibly happening, you know, in the data that I generated. And it's, you know, that has something to do with that kind of idea of like the unknown unknowns, and, you know, how are we accounting for these things that happen so rarely. And I think, you know, when we're talking about modeling, you know, potentially our model equations also don't allow for some of those things to happen. And, you know, that's kind of like, that it just sort of reminded me of that issue of, you know, is everything a tiny bit probable even though we've never seen it before? Or like, how do we account for, you know, that sort of like big surprise type of thing? And maybe that's allowing our models to, you know, co-evolve, or, you know, maybe that's linked somehow to that.
So that also made me think about how we can increase the knowledge of a process. So it's by increasing the amount of data, of the same data that we are already collecting, or it's by increasing the resolution of the data that we have, or it's putting more and different variables into a multivariate analysis. So how do we treat data to provide more knowledge than what we already have?
For this reason, I said the last sentence. For me, at least, the most important now is the quantification of information. We need to be sure that, or at least to be comfortable about how we are measuring the information. Because this way you can compare. Okay, maybe now you can choose different options. Okay, maybe I can do this, or maybe I need more information, or I need to discretize more. But really, you need to compare with something. So you need to quantify how much information you are adding with that.
Allison, your PDF example, first I thought you were talking about files, and then I realized you're talking about probability density functions.
Sorry, probability density functions.
But it's an interesting example, because first of all, I'm going to argue that in the same way as Bart Koskell, that a PDF is a mind projection. Okay, it's a model we impose on our data in order to try to explain it. And there's at least two problems there. One is the one you mentioned, which is where you don't have an observation in some part of the domain. And so you don't know what probability to assign there because you've never seen anything there. The other problem is you don't know if you've got the right number of dimensions to your PDF, right? There are inputs that you've never observed, which might be relevant and suddenly become relevant. I call the second one sort of an epistemic problem. And the first one is a kind of insufficient sampling problem, right? But you ultimately come back to, why do I have to use a PDF in the first place? And you know, Leonard Susskind, following Leonard Suskind's sort of argument, it would be that the reason I have to use a PDF is because I've got incomplete or unexplained information. I've got missing information. And so I'm, you know, if I had a deterministic relationship between three variables in 3 dimensions, but I don't measure one of those, and I can only project that into 2 dimensions, it's going to appear like a probabilistic relationship, even though it was deterministic to start with.
Isn't that the first problem, the insufficient sampling? You know, in particle physics, don't they use those to actually find new particles and stuff? They'll set up an experiment just through that probability density function, say, if this probability density function is correct, then we should observe a particle once every 50 years with this detector, you know, and sometimes they end up panning out. So would that be kind of, I guess if it's a mind projection, you can't ever show that it's true, but would that be in support of the probability density function being correct if you actually do get those additional samples to show that they fit maybe the tails of the distribution?
Correct, or a good enough description.
Yeah. Okay. Sorry. Yeah.
I mean, the challenge is we're always working with incomplete information, right? My argument.
I bet if I took all the data in the whole world, I'd still have some zeros in my PDF that I would always, you know, I would have to artificially attribute probabilities to them in order to allow them to someday happen.
Mm-hmm.
Well,
to be like, you know, that particle's out there.
Except that I could probably imagine that there would never be negative stream flows. Right?
Well, of course there would be. During an earthquake, you know, a landslide.
So a lot of it depends on our definition.
Oh, I see. Got it. Yeah. All right.
I think that, I mean, this is interesting. I think that one of the problems we have is we haven't organized going back to Praveen's question, we haven't organized ourselves in our processes by missing information and how much we need. That might be a thought process that we need to do in order to start building a better science. For example, you know, calculating the time needed for a rock to fall from one place to another may be something that we have already accomplished with a certain degree of, you know, accuracy. But conveying how climate change is going to be in 50 years is not something we have done, you know, 100% right, or predicting pandemics like the one what we are right now. So maybe something we need to do is organize ourselves. Like we have a collection of processes and how much information we still need to be able to somehow predict short or long-term consequences of those phenomena. Like Oshin and Praveen were saying before, and I think Jonathan mentioned, the duality between the physics and the data or information. It's actually, you know, there's a problem of scales. We probably have into the laws of physics, we have the principal components of, you know, the predictors and the predictants. But then when we move on to another scale, things might change and those relationships may no longer be valid, or there will be some other parameters that need to be added to that equation, some scale parameters. Think of it like the Hurst effect. The more information you get, the more data you get, the more standard deviation in data, and the scale range increases. Okay, those might be some of the thoughts I had in my mind after reading the paper.
If all of you agree, we are almost more than 1 hour we have passed. So if you want to contribute to the notes, you're welcome to use the spreadsheet that we have. And I think it's time to wrap up our session for today. So Andrew and Luis, would you like to wrap up the session?
Actually, I don't see Andrew or Luis here.
I'm here.
Oh, yeah. Oh, there you are. Okay.
Yes. But Andrew, I don't know. Maybe.
It seems much shorter than an hour to me.
I know. It was a nice discussion.
Oh, Andrew just slacked me. He's having connectivity issues.
Okay.
Okay.
So we can just continue, I think. He will try to make it back.
Okay.
One thing that I think it's important to mention in the situation of pandemics and then also hurricanes and nuclear reactors is a lot of times it's better to make no prediction than a wrong prediction. And I think making a prediction that a hurricane of a certain size won't ever hit this nuclear reactor could result in the reactor failing and catastrophic pollution, or making a prediction about the way a pandemic will evolve that's incorrect could ultimately lead to massive loss of lives. So I think these kinds of discussions are really good, and it's really important to keep them going. But when we are dealing with really important things, when we're making predictions, we need to be very confident in them.
A thought that comes up as you were saying that, Jonathan, is the issue of our desire to make things as simple as possible. My tongue-in-cheek comment is that the reason we believe that there's an underlying probability generating process in the universe that is simple is because our brains don't have enough storage capacity to imagine anything other than that. That's a little bit of a sarcastic comment. But related to what you were saying was, you've got a very complex process going on, and is it more, I think the comment is it more dangerous to use a very simple 3-state variable model to try to predict the behavior of the system when the actual number of state variables you need is something like 100,000? I think that's the question you're raising, is at what point does your modeling exercise become so simple, your view of the world is so simplistic that it's actually more dangerous than not doing anything at all. I'm not sure about that. I have to think about it.
I have to think about that statement too, that it's better to make no prediction. Because it also has, to me, it has a bit of a taste of the cop-out. Like, like you went to school, we paid you a long time, now you're a high-paid engineer or scientist, then you say like, well, it's better to make no prediction. And in a lot of cases, we're not in that position where that's an acceptable answer. I mean, maybe probably putting the bounds on, or trying to put a caveat on the prediction you make might be, I mean, I understand philosophically where your answer comes from. I'm just trying to apply it in the real world. That I'm not sure that
does this
a lot of people consider that an acceptable answer.
Does this relate to the idea that your predictions should be better than random chance?
Yes, I think so. And I by no means meant it to be a cop-out. I was a professional consulting engineer for 7 years, and I made a lot of predictions that resulted in infrastructure being built. And there's factors of safety and everything that goes into those. So I'm not saying that we shouldn't make predictions. What I'm saying is, if you have an observation that doesn't fit your model, and you ignore it, and your model ends up being incorrect as a result, then you should have a sense of consequence to that model. And
right. Yeah, I don't think we're as far apart as I made it sound, but it's I just mean, like, societally, it may not be that easy to make that response, right? Like, as a consulting engineer, most of the time you did end up giving them an answer, even though you didn't have all the information, right?
I wish I could stay, guys.
Yeah, I have to wrap it up too.
Yeah, me too.
Thanks, Lena. This was great.
Thank you, everyone.
What's the next paper that we're going to read?
I'm going to send the email.
Okay, perfect.
It's the network paper, I believe.
Okay.
I think so. Yes. And we are going to see each other on September the 30th. So
Perfect.
thank you, guys.
Bye.
Thanks for organizing.
Sure. My pleasure.
Thanks for joining.
Thanks for joining. Yes.
Bye.
Bye.
Right. Thanks, everyone.